Our next speaker is Dr. Eric Feron. Dr. Eric is currently a professor of electrical engineering at KAUST. Before joining KAUST, he served as a professor of aerospace engineering at Georgia Tech and MIT. His research interests span the use and development of methods in optimization, control, and computer science to address relevant problems in aerospace engineering and closely related fields. Today, he's going to give a presentation on Artisan engineering reinvented, 3D printing with structural requirements.
Welcome. Today's presentation is Artisan engineering reinvented, 3D printing with structural requirements. I am Eric Feron, a professor of electrical, computer, and mechanical engineering at King Abdullah University of Science and Technology. This work was performed with Kevin Garanger and Thanekon Kamvilai. The main topic of this presentation is how do you do 3D printing reliably? Here, unreliability of printed part can come with various grades of severity. In one case, the printed part may delaminate and then become very unreliable, maybe break. In other cases, the same part may just be subject to microscopic porosities, imperfections that, though they may not threaten the integrity of the part, may nevertheless greatly affect its mechanical properties. And in particular, for example, its elastic characteristics. So we decided to embark into trying to prove that it was possible to print parts with specific structural elastic behavior, even though the printer that's being used is incapable of doing so open loop. We simplified this question by formulating it as, can we print a cantilevered beam that meets precise elastic response requirements? The beam that we have here is wide but thin, and it is tall. The elasticity response requirements that we are interested in are a prescribed beam stiffness, informally defined as the ratio of the force measured at the tip of the beam to the displacement of the tip of that beam. Now, the idea to achieve this is to use feedback control by iteratively making measurements of the stiffness of what is being printed, devise what should be printed next, print the next set of layers for the beam, and then iterate. Because there are measurements made at regular time intervals, and that what is printed next is a function of all past measurements, and all this is done in an iterative fashion, it is indeed a case of feedback control over a finite horizon. In order to demonstrate our work, we chose a low-cost 3D printer together with a force sensor that we use as a feedback mechanism. Mounting the force sensor on the printer arm gives us the possibility of transforming the printer from a pure actuation device to an actuation and measurement device, a primitive form of robot, if you will. The process by which we establish closed-loop control over the printing process relies on a model of the beam. The model of the beam obeys Bernoulli's equation and is relatively simple. The main parameter that drives the stiffness model for this beam is the width of the beam. The beam is printed as a superposition of rectangular sections with given wall thicknesses and the corresponding infill material inside the beam. With this kind of formulation and this kind of manufacturing, we use the standard Young's modulus and beam moment of inertia parameters in order to obtain the beam shape given the boundary conditions, which include the fact that the beam is cantilevered on the one hand, and that the tip of the beam to which the force is applied is free on the other hand. The discrete model of the beam is what allows us to insert it into a computer-driven logic. The beam, the discrete version of the Bernoulli equation gives us the displacement of the beam as a function of the layer considered. If we have n layers, d is the displacement at the tip of the layer, given that a force is applied on top of the beam. The parameters that are important in order to understand the behavior of the beam are a mix of the force that is being applied, the Young's modulus, and the moments of inertia. The rectangular nature of the beam section, together with the walls of the beam, tell us that really, if you will, the combination of the Young's modulus and the moment of the beam, the bending moment of the beam, is an affine function of the width of that beam. And that is because the width W of the beam, which is along the y-axis, is variable, while its thickness is not. And the width of the walls remains, the width of the surface of the beam remains constant. As the beam gets increasingly narrow, the side walls remain intact, thus making the beam's bending characteristics per unit length affine in the beam's width. So to build that model and specify the unknown parameters, we simply extracted a model from a few basic specimens that you see printed here and whose stiffness was measured using our experimental apparatus. Without any further detail, let's talk about the beam building dynamics. So the key is to be able and capture the beam's building dynamics as a linear system. So how does it work? Well, the state of the beam is at any point during its construction, the width or something related to the width of each layer of the beam. Now, it could be the width of the beam or the inverse of the width of the beam, or maybe a noisy version of this, given that, well, there are always noises present in the building process. Here, we have chosen to work with the inverse of the width of the beam as opposed to the width of the beam. And what you see in the recursion shown in figure 5 is basically the beam width inverse adding up one after the other as a vector, and that constitutes the state of the beam. Now, all these states are not exactly measured because, well, we do not necessarily have precise measurement of this width. These widths are just those that are commanded to the printer. But as we know, the process is very noisy. As a consequence, we then need to obtain the best possible estimate of what the beam's state is. And that makes us relate the state of the beam to the output, the measured quantities about that beam. And the measured quantity is its compliance. That is the ratio of the displacement measured during the test to the force applied to the sensor. And this constitutes new information, which is linear in the state of the beam, and that we can use in order to improve our knowledge of the state of the beam seen as a stack of rectangles stacked up on top of each other. In order to simplify things, we linearize everything involved in our process. In particular, we linearize the compliance measured at any stage to make it a linear function of the measured state subject to noise. Now, when we have a model of the beam building process as a noisy process, which is read by noisy measurements, we have the ingredients for making a state estimator, which is not much different from a traditional Kalman filter adapted to the time-varying dynamics of the beam, since the state changes at every time step. Without going into further details, once we have the estimate on the beam's state, we can then talk about controls. What is the control activity about? Well, the control activity is about designing the next steps, the next layers of the beam, given what has been printed before. So we have a number of objectives to meet. For example, maybe minimize the amount of filament that we are going to use, maybe minimize the irregularity of what is being printed in terms of the difference between the width of the beam at different stages. We may also have, because we're working with a pretty low quality printer, a requirement that no overhang appears. And once these objectives are added up and all the constraints are included, including the no overhang constraint on the one hand, and then perhaps the most important constraint, which is that in the end, we should have a beam whose compliance is the one that is being asked for, we can solve the corresponding optimization problem. And we solve this optimization problem at each time step that is between the pass printout of a few layers and the next printout of a few layers. We solve this optimization problem that tells us, in principle, how to print all the remaining layers. However, what we do is we print only a small batch of the remaining layers, allowing ourselves to take yet another measurement afterwards and repeating the process, which gives us the opportunity to enjoy the benefit of feedback, which is continuous correction of what is being printed based on what is measured. So the experiment was to print a cantilevered beam with a prescribed bending stiffness, which was chosen to be 8.3 grams per millimeter. Imagine a beam whose height is about 10 centimeters, whose width is about 2 centimeters, whose thickness is about 2 millimeters, and you got a good idea about what is being printed. Let's see the results. Using our proposed control law versus what I would call open loop printing. So we chose to print a number of specimens, 3 of them open loop and 3 of them closed loop. To print the 3 open loop specimens, we simply run the optimization problem that I mentioned a couple of slides ago. Only once we looked at the stiffness, at the width that needed to be printed from bottom to top of the cantilevered beam, and we printed them. We have measured the stiffness of the partially printed beam as it is being built up, but we did not use those measurements. The net result, however, is the more pale response that you see as the number of layers adds up, which starts with high stiffness because the beam is very short. And as the layers are added and the measurement keeps being taken at the top of the beam, get lower and lower, corresponding to intuition that the taller the beam, the less stiff it is. We compare this with a closed loop implementation whereby the measurements are used at every stage so that the next layers of printing are dynamically chosen based on those measurements. the target stiffness, once the beam is fully printed, is shown on this graph. And what can be seen both to the left and in more detail to the right is that indeed there is an improvement provided by checking in real time the characteristic of the beam that has been printed. In particular, we see two things. First of all, the open loop printout misses, on average, the target stiffness, which is 8.3 grams per millimeter. Now, on top of that, it is also quite dispersed. That is, the standard deviation of the printout stiffnesses is pretty large in comparison. The same stiffness measurements, once the beam is printed, when it has been printed in closed loop, show a much more precise target stiffness, or to be more precise, a much more accurate stiffness compared with the target stiffness, and less dispersion of the stiffness that have been eventually reached during the printing process. So, as a discussion, well, it's a story about feedback control. It's a story about feedback control used in a new framework, or to be more precise, a new kind of application. And it shows what feedback control can achieve. In this particular case, well, there is no doubt that the model that we have devised by measuring Young's modulus together with the moments, or the effect of the moments of the beam cross-section. And nevertheless, despite these imprecisions, we can beat the uncertainty associated with the model with an improvement of average stiffness compliant of 94%. Now, we also have disturbance rejection because we are able to reduce the standard deviation of the final printed product from 1.3 gram per millimeter to 0.24 gram per millimeter. That is an 80% improvement. In terms of timing, well, it takes about 3 hours to print a part. Open loop. Closed loop, it takes about 3.5 hours, and corresponding to about 3 hours to print and much less time to think, make measurements, estimating the state of the beam, and deciding what to print next. So there is, as additional remarks, that we see there is an essential role of optimizing at each time step. However, this optimization, which happens to be convex, can be done relatively quickly. In terms of further work, we can immediately think that it would be interesting to extend the work to multiple structural and geometrical constraints, maybe include dynamical structural constraints as opposed to static structural constraint. The question is then, what should be the sensor? What should be the excitation mechanisms? I conclude this talk by thanking the National Science Foundation and the Air Force Research Lab who sponsored this research, and in particular, Dr. Kay-Ann Hobbs and Dr. Dan Berrigan from the Air Force Research Lab. thank you very much. And I am now waiting for your questions.
Thank you, Professor Feron, for the interesting presentation. We have one question from the attendee. Can you see the question?
Let's see. So should I? Very good. Yes, so the question is, did you consider the cooling time and temperature fluctuation in the feedback control process? Actually not. So we did not wait for the system to cool down too much, but this is an excellent question. I believe it was already asked to me in earlier times when I gave this presentation. And in a way, there is that we could see that as an interesting benefit of feedback control, that we do not necessarily have to wait for this because maybe the cooling down process will happen a little bit later. And so after we have printed a few further layers, but then we nevertheless make a measurement, and that measurement about the layers having sort of, in a way, changed state, and maybe the beam having changed characteristics as it has cooled down during the printing process, then can be accounted for by the further measurements that have been done. So on the one hand, we have not done it. On the other hand, I claim that nevertheless, we can still enjoy the benefits of feedback and implicitly account for these effects.
Okay, thank you. Thank you, Professor Feron. There is no more questions. I hope we can wind up this talk.
Ragesh, I have a quick question for Eric. We have a few minutes. Thank you very much, Eric, for your presentation. What do you think could be improved in terms of instrumentation of 3D printers to give the right feedback? Because what I mean here, you equip the head with force sensors, but I mean in terms of control. So what do you think would be the right way to improve 3D printers to give the relevant information for what you are doing?
So what I was thinking about is, for example, maybe having sensors that sense like dynamic behaviors as opposed to static behaviors. On the other hand, that raises a question about, well, how would we excite a piece of something that's printed while it is being printed? So you could imagine like putting a vibration table on of the kind I asked you for on the printer. So that would probably change a little bit the way we may even want to design the printer. There is maybe we should, and again, this is just speculation, but maybe we could use printing arms like I've seen instead of the rather low-cost printer that I've been using. Really the only thing that I wanted to show here is that we could reach a certain level of accuracy in what is being printed, even when you use like a very low-cost printer. And you may have noticed that the sensor alone was half the price of the printer. So I don't know if that answers your question, but it seems to me that what you would want is mechanisms. If you follow only structural requirements, you want to have sensors and actuators that will allow you to really like poke into the printer, just a little bit like, for example, as something I've seen about people like testing the bell that they build, except that when they build bells, they usually remove material. They don't add material.
Okay, thank you, Eric. Thank you.
Okay, thank you, Professor.
Thank you.